Hello and welcome to today's lesson looking at the concept of pressure. Now today's lesson, which forms part of the AQA Separate Science topic of forces in the physics course, we're going to look to try and understand the calculated pressure. So what are we going to look at in today's lesson? We're going to try and define fluid and surface pressure, calculate fluid and surface pressure, describe how a difference in pressure can produce an upthrust on an object, and detail and describe the properties of atmospheric pressure, which falls into the following part of the GCSE specification. So we're going to be looking at pressure in a fluid, which links to the pressure and pressure differences in a fluid, which is found in the forces topic of AQA GCSE Physics. Now please note that both this part of the specification and this part of the specification, which we're going to look at in today's lesson, is separate science only content. So if you were carrying out GCSE combined science, you would not have this as part of your specification. So there are two main types of pressure found in the real world. We've got surface or solid pressure, which is the pressure exerted when a solid object places a force upon a surface, and fluid pressure, which is the pressure exerted when the particles of a fluid collide with the surface. Now in this particular module, we're going to focus on fluid pressure. Now fluid pressure, like we said before, is the pressure exerted when the particles of a fluid collide with the surface. Now a fluid can either be a liquid or a gas. It is a substance that can flow, that can move. Now in a fluid, the particles have a random motion with a range of speeds. This means that in a fluid, in this particular example, the particles are moving around. So as a result, as they move around, they will collide with the sides of the container or surface as they move around. Now as all sides will have roughly the same amount of collisions as the particles are moving around randomly. Now this particular collision will cause a pressure in the fluid. So the collisions of the particles with the side of the container or a surface will cause a pressure in that particular fluid. Now the pressure always acts outwards for a fluid, and in the fluid the pressure produces a force normal to the surface or to the container. So what that means is the force is at right angles to the surface the pressure is exerted upon. So it'll look something like this. So fluid pressure is the pressure in a liquid or a gas, and it's exerted when the particles of a fluid collide with the surface. Now the pressure in fluids causes a force normal or at right angles to any surface that it collides with. Now we can work out pressure with the following equation. That pressure in pascals is the force normal to the surface in newtons divided by the area of that surface in meters squared. Now the units of pressure can also be expressed in terms of force and area. So for example, when the force is in newtons and the area is in meters squared, the unit of pressure is newtons per meter squared, which we commonly call the pascal. But when the force is in newtons and the area is in centimeters squared, the unit of pressure is newtons per centimeter squared. But when the force is in newtons and the area is in millimeters squared, the unit of pressure is in newtons per millimeter squared. So the unit of pressure is the unit of the force divided by the unit of the area. Now this particular equation is very important, and it must be memorized for your examination. Now you can convert an area given to you in a question into meters squared to find the pressure in pascals. However, some questions will ask for the pressure in different units, so just be aware of that. Now you'll also be expected to rearrange this equation to make the area or the force the subject of the equation. Now the most common rearrangement of this equation is to say that force normal to a surface is equal to pressure in pascals times by the area of that surface in meters squared. Now remember, a resultant force can cause a change in pressure. So actually we can write it as the following. Resultant force is equal to change in pressure in pascals times by the area of the surface in meters squared. Now that will be important for later on in this particular lesson. So here's an example calculation. A gas inside a container applies a force of 400,000 newtons, and the wall of the container has an area of 8 meters squared. Calculate the pressure of the gas. Now we can calculate the pressure with the following equation. pressure equals resultant force over area of the surface, so it's 400,000 divided by 8, so it's 4.0 times by 10 to the 4 pascals. Now please note that in our answer, we're going to give our answer to the correct units and to the correct number of significant figures. Now, we can consider fluids like liquids and gases to be in open to closed systems. So can we understand if a system is open or closed and why? Well, for example, let's look at this one. Water in a bottle. Well, this is a closed system since when the lid is screwed on tight, the water can't escape the system and no water can join the system. What about water in a pan? Well, that would be an open system since water can escape from the pan or it can join into the pan if needed. What about water in a lake? Well, this one's going to be an open system since water can join the lake or it can leave the lake freely. What about water in this tank? Well, this will be a closed system since water can't join the tank and it can't escape the tank. What about water in an ocean? Well, this would be an open system since water can escape the ocean but it can also join the ocean. Now in today's lesson we're going to focus on the property of pressure in an open system, so like in lakes and in oceans. Okay, now let's have a look at a particular example of an open system situation. Now you look at this particular picture and it's showing you a dam. Now this dam is obviously holding the water of this open system in place. Now look at how the dam is constructed. Why does it have the following pattern of construction? Well, dams are constructed with a thicker wall at the bottom and a thin wall at the top of the dam because fluid pressure changes in an open system. This is a fundamental concept of pressure. Fluid pressure changes in an open system, but the fluid pressure stays constant in a closed system. Now we've covered the closed system concept in the particle model of matter unit covered earlier in the course. So we're going to focus on the open system. Now in the open system, there's a low pressure at the top of the liquid, so you need a thin wall for your dam, but there's a high pressure at the bottom of the liquid, which requires a thick wall for your dam. So fluid pressure increases with depth in an open system. So as you go further and further and further down in a body of liquid with an open system, the pressure gets bigger and bigger and bigger and bigger. So in an open system like an ocean, again, the pressure of a fluid increases with depth. So you've got a low pressure at the top of your ocean, but at the ocean floor, you've got a high pressure. Now, as particles move around, they collide with each other and produce forces at right angles, like we mentioned before. Now, the downward force of all these particular collisions is weight, and the further down you go, the more particles there are above you, so the greater the force of weight is pushing down because there's more particles exerting a force downwards, so therefore there's a high pressure at the bottom of the ocean and a low pressure at the top of the ocean, because the lower you go in a liquid, the force being placed downwards increases as an accumulative effect from the particles above. Basically, the lower down you go, the more particles there are above you, so the greater the force exerted downwards of the weight. So, at the top of the ocean, there are only few particles above this point, so the weight pushing down is low, but at the ocean floor, there are more particles above that particular point pushing downwards, so the weight pushing down is high. So what do we know? The weight of the water acting downwards on objects increases with depth, so the pressure acting downwards on objects increases with depth. So the lower you go in a liquid, there are more particles above you pushing downwards from collisions, so you get that particular pattern. Now, at any horizontal line in this diagram, okay, the number of particles above that point is roughly the same, so the weight acting down is roughly the same, so the pressure is roughly the same at any point along these horizontal lines. So along these particular lines, you have constant pressure. Now, when it's considered in air, a horizontal line of constant pressure is called an isobar, which you may have heard about when you've watched the weather forecast before. Now, it's important to note that areas of different pressures can exert a force on objects in the fluid. Now, if you're at the bottom of the ocean, a force is exerted downwards, pushing you down. Now this links into something we talked about earlier, that basically if you have a difference in pressure, a force is produced, or you can say a difference in pressure produces a resultant force, or you can also consider it by saying a resultant force causes a change in pressure. So the force can be calculated from using the previous equation which we talked about, which is that the resultant force is equal to the change in pressure times the area, which comes from the equation pressure equals resultant force over area. So if you have two parts of your fluid with a difference in pressure, you will have a resultant force produced from that difference in pressure. Now again, this particular equation has to be memorized for examination. It's the same equation we looked at earlier. Okay, so this equation is calculating the resultant force or the change in pressure between two parts of an open system. So let's get this right. In an open system, the fluid pressure increases with depth because the further down in a fluid, the greater the amount of particles above that point producing a force downwards. In an open system, the fluid pressure is constant in a horizontal line at the same depth because along this line there's the same number of particles producing the same force pushing down, and a difference in pressure can result in a resultant force on an object, which can be calculated with the equation resultant force equals change in pressure times by area. So let's look at this particular example. So in this demonstration, the cylinder is filled with water all the way to the top of the cylinder. All three holes there are currently filled up, but what would happen if we open these particular holes in the cylinder? Well, you'll see the following. At the top, there's a little spurt of water. Why is that? Because there's a low pressure. What do you notice at the bottom? A large spurt of water because there's a higher pressure, because in an open system, such as this cylinder, the pressure increases with depth. So you get a lower pressure at the top because there's less weight above it pushing it down, but you get a large spurt of water and a high pressure at the bottom because there's more weight above it pushing it down, which we can see in this particular example. So, if we consider this in terms of oceans, basically we consider the top of the cylinder to be like the top of the ocean, which is where we are normally. Okay, so that's the low pressure, and at the bottom of the ocean, the bottom of the cylinder, you've got a high pressure. So again, we can link it back to our previous diagram in the discussion of oceans, which we talked about before. So we can calculate the change in pressure with the following equation. So whilst we can also calculate change in pressure by doing force divided by area, there's another equation we can use, and that is the change in depth in meters times by the density of the liquid in kilograms per meters cubed and the strength of gravity in meters per second squared. If you times all three of those values together, you can get your pressure change. Now this equation is given to you in your examination, but what you're not given are the units or the situation to use this in. This can only be used for a fluid in an open system, and this calculates how the pressure changes when an object moves from one position to another position in an open system. So again, you've got to remember these particular ideas that can only be used for a fluid in an open system. So this particular part of the equation, just saying pressure equals depth times by density of a liquid times by strength of gravity, calculates the pressure at one point in the fluid, whilst the other equation can calculate the pressure change when you move from one point in an open system to another point in an open system. And like mentioned to you before, you are given this equation. It is in your examination book, but you've got to be able to use it and to remember what the units are for each value. So here's an example calculation. Calculate the pressure due to seawater of density 1050 kilograms per meter cubed at a depth of 200 meters. Well, pressure equals depth times by density times by strength of gravity. Now we know on planet Earth that the strength of gravity is 9.81, so we know that the depth is 200 from the question, the density is 1050 from the question, and the strength of gravity is 9.81. Multiply the three values together and you get an answer of 2.1 times 10 to the 6 pascals. Now note again, we give all our answers to correct number of significant figures and we give our answer with the correct unit. Now we can link the concept of fluid pressure to density and the idea of floating and sinking. Now we know the density of an object determines if an object will float or sink. So if an object is less dense than a liquid is submerged in, it will float. If the object is more dense than the liquid is submerged in, it will sink. So why does density determine this? And how does this link into forces on an object? Well, whether an object floats depends on the forces of upthrust and weight. An object floats if upthrust equals weight, because the forces on the object in the vertical plane are balanced, so there's no resultant force, so therefore it will float. But an object will sink if the weight is greater than the upthrust, because the forces on the object in the vertical plane are unbalanced. There's a resultant force downwards, so it sinks to the bottom. Now, just to clarify something, if upthrust were greater than weight, then the object would actually accelerate out of the liquid, because there'd be a resultant force acting upwards, and the resultant force causes an acceleration. This couldn't happen due to how the forces are produced, so that scenario doesn't take place. Now, what causes upthrust to be produced on an object immersed in water? Well, it all links to fluid pressure, because when an object is in water, there's a greater pressure on an object at its bottom than at its top. There's a difference in pressure between the top of the object and the bottom of the object. What do you get when you've got a difference in pressure? You get a resultant force, and that is upthrust. So to clarify, because we know in an open system that the pressure increases with depth, that there must be a higher pressure at the bottom of an object submerged in a liquid compared to that at the top of its object. So therefore, we've got a difference in pressure, so therefore we've got a resultant force, and so therefore upthrust is produced. Now, the force always is exerted from the high pressure to the low pressure, so it's always acting upwards, which gives its name upthrust. This also is the same effect which explains wind in the air. So for all liquids, pressure increases with depth, because the further down you go, there's the more particles above it pushing it down, so therefore you get your concept of upthrust. So an object that is less dense than the fluid it is in weighs less than the equivalent volume of the fluid, so this means it displaces a volume of fluid that is equal to the rate to get upthrust to equal weight before it is completely submerged. But an object that is denser than the fluid is placed in weighs more than its equivalent volume. This means the object is unable to displace enough fluid to equal its weight. This means the weight is always going to be larger than the upthrust, so will always sink. So just to clarify this one more time, when an object is in water, there's a greater pressure on the object at its bottom than at its top, because there's more particles above at the bottom pushing down compared to that at the top. So there's a difference in pressure. The one thing a difference in pressure produces is a resultant force. So we've got a resultant force acting upwards, which we call upthrust. So that's a very important idea. Now, we've covered pressure in the depths of liquids, but how does pressure change in the gases of atmospheres? So we're going to look at how pressure changes in the atmosphere. Now, the atmosphere of the Earth is one of the most amazing aspects of the planet. It's a mixture of nitrogen, oxygen, and other gases. Now, the first atmospheres of the Earth were mostly carbon dioxide and methane from the first volcanoes, but over time, photosynthesizing plants meant that the amount of oxygen went up and nitrogen was also released in different reactions. And our atmosphere also protects living things on Earth from the sun's harmful or ionizing radiation such as UV, X-ray and gamma radiation, and it's predominantly carried out by the ozone layer in the Earth's atmosphere. Now, the atmosphere is only about 100 kilometers from the surface of the planet, which actually is tiny compared to the size of the Earth itself. If the Earth was the size of a basketball, the thickness of the atmosphere could be modeled by a thin sheet of plastic wrapped around the ball. Now, the atmosphere exerts a pressure, what we call atmospheric pressure. Now, at sea level, that is 1 atmosphere, or approximately 101,000 pascals. But how does the air, which is a gas, a fluid, produce a pressure? Now, if you live in the atmosphere of the Earth, you're constantly surrounded by the particles of the air. Now, these are gas particles moving about at random, with a variety of speeds in random directions. Now, in this motion, some of the particles will collide with the objects present in it, so this will produce a force, and because, as we know, pressure equals force over area, this will produce a pressure which we call the atmospheric pressure. Now, whilst they seem like different effects, liquid pressure in the ocean and gas pressure in the atmosphere are the same effect. They're both examples of fluid pressure. Now, like the famous scientist Evangelista Torricelli stated, we live submerged at the bottom of an ocean of air. We live in a region of low liquid pressure but high gas pressure, because we live at the top of the ocean. okay, which is the liquid pressure, but at the bottom of the atmosphere, the gas pressure. So if we consider our previous demonstration in terms of oceans, we could model it like this, but if we consider it in terms of the atmosphere, we are actually at the bottom of the cylinder. We are at the bottom of the atmosphere, and at the top of the atmosphere, there's a lot lower pressure like there was at the top of the cylinder, but it's exactly the same effect as that of the ocean. Now, the atmospheric pressure works in the same way as fluid pressure discussed previously. Now, the higher up you go, there are fewer particles pushing downwards because there's fewer particles above those points exerting a weight downwards. But at the bottom of the atmosphere, close to the surface of the Earth, there are many particles above those points exerting a force downwards of weight. Okay, so you've got a low pressure at the top of the atmosphere and a high pressure at the bottom of the atmosphere. Okay, so as a result, we're links it through like that. So there are fewer particles, okay, at this point because there are fewer particles above this point pushing down, exerting a pressure downwards at the points. The higher up you go, there's a lower pressure. But there's also a second reason, which is unique to the atmosphere, which isn't found in the ocean. The other reason as to why the pressure is lower at the higher altitude, at the top of the atmosphere, is because there are just less particles higher up you go in the atmosphere. The atmosphere becomes thinner the higher up you go. So we can say it as the particles are further apart. So there are actually two reasons why the pressure will change: the number of particles present and the amount of force acting downwards. So we can use a very similar equation to work out the pressure in an atmosphere. We can say pressure equals height times by density of gas times by the strength of gravity. Again, it's the equation of pressure for fluid in an open system, and it's the same principle as the one we use for the ocean. So although we measure the height from the surface when we calculate atmospheric pressure and not depth, it means we can say that atmospheric pressure decreases with height. So at the high heights, okay, the pressure of the atmosphere is low, but at the low heights, because the distance from the surface is low, the pressure is high. Why is the pressure lower the higher up you go? Well, firstly, there are fewer particles above that point producing a weight downwards, and secondly, there are less particles there are fewer particles, the particles are further apart, so there are less collisions anyway, so the force of the effective pressure is going to be lower. So let's just clarify what we have learned. Atmospheric pressure is created on a surface by air molecules colliding with the surface. The greater the number of particles above a point, the greater the weight acting down, the greater the pressure. In addition, there are fewer particles higher in the atmosphere producing this pressure, so as the height increases, the atmospheric pressure decreases. So what have we learned in today's lesson? That a fluid can be either a liquid or a gas, and pressure in fluid is caused as a force normal to any surface caused by the collision of the gas or liquid particles with the surface or with the container, and we can calculate the pressure by saying pressure equals force over area. Now, the pressure due to a column of a liquid or a gas can be calculated by saying pressure equals height times by density times by gravitational field strength, and this equation is given to you in your examination. And then you should also be able to calculate the differences in pressure at different depths in a liquid, and that a partially or totally submerged object experiences a greater pressure at the bottom than at the top, which creates a resultant force upwards, which we call upthrust, which links into floating and sinking. So if you've learned in today's lesson, we can define fluid pressure and surface pressure, calculate fluid pressure and surface pressure, describe how the difference in pressure can produce upthrust, and then detail and describe the properties of atmospheric pressure. I hope you've enjoyed today's lesson looking at pressure in the fluid. In the upcoming lessons, we're going to look at atmospheric pressure in a bit more detail. Thank you very much and have a lovely day.